What we will cover in this section. First, we'll summarize qualitative variables with frequency and relative frequency tables. We'll display those data in bar graphs and pie charts. Then we'll summarize quantitative data with frequency and relative frequency distributions. And finally, we'll display the frequency distribution using histogram, frequency polygon, and cumulative frequency polygon. Displaying qualitative data. So as we discussed in the previous lecture, there's two types of data, qualitative and quantitative. Here we'll be looking initially at the qualitative types of data. We'll represent this data in three ways: bar chart, pie chart, and a Pareto diagram. Quantitative data is displayed in a very different way, which we'll discuss later on in this lecture. Describing qualitative data. So we'll be using bar charts, pie charts, and a Pareto diagram to look at different types of qualitative data. Let's start with a frequency table. A frequency table is a grouping of qualitative data into mutually exclusive and collectively exhaustive classes, showing the number of observations in each class. Let's think of this as an example. Imagine you run Prime Pizza or Pizza Primes, and let's say you're interested in their beverage preferences. And this is important to know as you order the syrups for these beverages on a regular basis. So you give out this survey to a random 100 customers, and you have a large spreadsheet when each of their preferences are filled out. Once you complete that large survey, then you start to take each data point and you start to summarize it in a frequency table. For example, when you looked at your sample, you saw that in terms of Cola Plus, 40 out of your 100 customers liked that choice. Coca-Cola, you had 25 out of 100 customers that liked that choice. Now let's see this represented in a bar chart. Here's a bar chart representation of the frequency table we drew. So you can see here that Cola Plus had 40 customers that chose it, and here's the bar representing that. Coca-Cola had 25, you can see that here, well represented on the bar. Pepsi 20, and Lemon Lime 15. This bar chart in particular is in fact a Pareto chart, because you notice that the data is organized in descending order from left to right. And the reason that this is done is because typically when we're looking at Pareto charts, we're trying to understand the highest priority issue. And in this case, you'll see that since we read from left to right, this most important component or the most frequent observation is also over to the left. This is a new type of bar chart representation. This is on YouTube. They're called racing bar charts. This one in particular is showing the most popular television show from 2009 to about 2019. There's so many different varieties of these. It's just a really fun way to look at graphics. All right, what about when we're drawing a pie chart? Well, to draw a pie chart, what we need to do with our frequency table is also show it in terms of relative frequency, or in this case, relative percentage. So when you want to go from frequency to relative frequency, all you would have to do is take the frequency in a given class and divide it by the total number of observations. And if you want to convert it into percent, you will want to multiply it by 100. So in the case of Cola Plus, we had 40 people that preferred it over 100, right? And that as a percentage becomes 40%. So we have 40%, 25%, 20, and 15. And then we have this resulting pie chart. Displaying quantitative data. So the types of data, again, qualitative and quantitative. Now we're looking at our quantitative branch. So in the case of the qualitative data, remember we were looking at measures of levels of measurement of nominal and ordinal level. For quantitative data, we're now looking at interval and ratio level data. So the three types of charts that we'll look at to display our quantitative data is a histogram, a frequency polygon, and a cumulative frequency polygon. In a later section, we'll also be covering box plots as well. So one thing that we want to think about is, why do we want to see a distribution? Why do we want to see it displayed? And there's 4 different things that we look for when we're trying to describe a distribution. That acronym is going to be SOX for shape, where we describe the shape of the distribution in one of 2 ways, symmetrical or skewed. Second is outliers. Is there any data that is unusual and doesn't seem to fit the rest of the overall pattern? Center, we'll look at the typical value as more of a summary of the whole batch of numbers. So this would be our single value that describes the entire distribution. Think of this as the mean or median. And then the spread. Since we know not everyone is typical, we also need to talk about the variation in the distribution. So we need to see if the distribution is tightly clustered around the center, or is it spread out, making predictions from the distribution more difficult. Let's start with a histogram. A histogram is a plot that lets you discover and show the underlying frequency distribution of a set of continuous data. This allows the inspection of data for its underlying distribution, if it's normal, outlier, skewness, etc. The SOX we described in the previous slide. This is just a recent histogram of, here it says last week's job openings growth slow, well below the average. So this is week on week changes in number of job growth. So this week's was, as March 13, 2020, was negative 89,000, which is well below our average. So let's look at an example. We're going to look at a specific example from what's called Applewood Auto Sales. This is just a randomized data set just to help us understand how to create a histogram. So this, what you're looking at, this jumble of numbers, this is your raw data. Looking at this raw data, we want to answer the following questions. First, what is a typical profit on each sale? So the central point. What's the largest or maximum profit of any sale? This is more about your spread of your distribution. What's the smallest or minimum profit of a sale? And around what value did the profits tend to cluster? Now, none of us can look at this raw data set and be able to imagine all of those values. The only thing we can see off this chart is that the maximum is 3,292 and the minimum is 294. So let's start off by creating this histogram. This is going to be a several-step process. Creating a frequency table for continuous data. So unlike our qualitative data, where each category was very clearly known to us, and we can take each item and put it into a mutually exclusive category. However, when we have continuous data, we don't have clearly defined categories to fit our data into. And for that case, we need to create classes or bins in order to create certain intervals for us to measure our data and put them into each different grouping. So a useful recipe to determine the number of classes or bins is using what's called the 2 to the k rule. So what we're doing in this case is we're rising 2 to the kth power that basically is going to be greater than the number of our observations, typically greater than it by the smallest amount. So let's try it for our sample for the Applewood auto sales. So N is 180. So all we have to do here is a process of trial and error. So let's start by testing out 2 to the 6th. Well, 2 to the 6th is equal to 64, and that doesn't generate enough data for us. That's not enough bins. How about 2 to the 7th? Well, 2 to the 7th is 128. Again, that's below the number of our observations, so we can't use that. When we go to 2 to the 8th, that's equal to 256. This number itself is irrelevant, but we know that 2 to the 8th is greater than 180, and therefore we will use 8 classes in this example. If we wanted to have n of 100, if we had 100 observations, then we would use 7 classes because 6 classes doesn't quite reach the number of observations, and 8 is too many. Now, why is it important to have these distinctions? Well, if your bins are too small, as you can see in this example, you get this really not very nice looking distribution that you can't really say much about. And if they're too big, you lose a lot of information. So this recipe, 2 to the k, gives us a much better picture of the distribution because that's what's most important. Let's go to step 2. Step 2. Now that we've created the number of classes, we move on to figuring out how large each interval should be. So how big is each bin? So now, in this case, to determine that, we have a rule again. And this rule basically says the interval for a bin or a class should be the highest observation minus lowest, so maximum minus minimum, divided by the number of classes that we established in the previous step. In this case, it was 8. So in the Applewood data set, the largest observation was 3292 and the smallest was 294. So when we plug that into the equation, we get an interval of 374.75. Now, the point of a histogram or any kind of graphical representation is to simplify the results for it to be easy to understand. And at 374.75, that's a weird number to put into a graph. So in order to basically adjust a little bit, we're just going to round that to 400. Now, is that necessarily important? No, it makes it a little bit easier. For example, we could have also used 375, but in that case, you'd have to be working with adding and basically adding these odd numbers, and your class titles or bins would be a little bit more messy. So when possible, it's good to use round numbers, but that will not always be the case. Now, one very important rule here is that you never want to round down the interval. You can round up, just not round down. Because if you round down, then that's going to impact the amount of data in each of your classes, and you may not effectively be able to fit all your data into the number of classes you were looking at. Step 3. Step 3 is finding the lower limit of the first interval and set the individual class limits. So in our data set, our data lowest point was 294. So since we rounded up the class to 400, we can round down our interval to start at 200 and go to 600. So this would be our first bin. Our second bin would be 600 to 1000. Now you may ask, well, what if I had an observation that was 600? What class would I put it into? Well, if this is class 1 and that's class 2, think of class 1 ending at a point like 599.9999, right? Since it's not clear how since it's not clear where the change is from 600 to 601, we basically assume that the class 1 will end at 599.999 and class 2 will start immediately at 600. Now this is very different. For the very last class, whatever the last number is, that's where that class will end. So if you had an observation of 600, you would place it in class 2. After we establish our values, the next step is to tally the auto sales profits into each class. So it's just counting. So we count how many in each class, and we basically create our frequency. We can also generate a class relative frequency, which is the class frequency divided by n, just like we did before with the relative frequency. And if we want to convert it to percentages, we just multiply that frequency by 100. Let's have a look at our frequency distribution. So here's our data. In the first class, for the 200 to 600, we have 8 observations. In the second class, 600 to 1000, we have 11 observations. Third class, 1000 to 1400, we have 23 observations. And you can see that when you add up your frequency, that should equal the total number of observations in the data set. The relative frequency, right, is just in the first one would be 8 divided by 180. So you can see that 4.4% of the data is represented by the first class. And what's our biggest class? Well, that would be this class here, 1800 to 2200. This represents 25% of our observations are within that class. So what is that telling us? It's telling us that 25% of all the cars sold generated a profit between 1800 and 2200. Let's see this in graphic form. Here's our histogram. So let's talk about our SOX acronym here. SOX. Shape, outlier, center, and spread. So first let's start with the shape. Right? Looking at this distribution, you can see that it's not perfectly symmetrical, and therefore we're going to call this a skewed distribution. Okay, so there's a slight skew, and since this tail is longer here on the left side of the distribution, this distribution also is a leftward skew. We'll be measuring this with an equation and so on in a later section. Outliers. Do we see any outliers in this distribution? Well, the answer is no. We don't have anything that is distinctly outside of the pattern of this data set. An outlier would be something like if there was maybe a gap here and then there was some profits over 4,000 here off on the corner, like a separate bar. That would indicate an outlier. Center. We could see the center is here somewhere, right? In our most frequent set of observations. So here, this 1800 to 2200, that would be basically our center. If we were to guess the mean of this distribution, it would be somewhere within that range. And then spread. Now, typically it's a little bit challenging to identify the spread when you don't have something to compare it to. But again, since we don't have a lot of gaps between our areas, and you can see a fairly strong, consistent shape here, and it was almost symmetrical. It's pretty clear that the spread tends to be very closely clustered around the center. Okay, variety of histograms. So this is a histogram here that has a small data set. This is a histogram with a slightly larger data set. And this is a very large data set. What's happening here? What's changing? Notice that this little step ladder type of pattern tends to kind of disappear and smooth out as your data set gets larger and larger, almost becoming curve-like. Now keep this in mind. If you've ever seen one of these normal distributions, again, slightly bad picture, but if you've ever seen one of these normal standardized distributions, these distributions basically always imagine that there's a histogram underneath that distribution. It's just based on so many observations that it has become smoothed out. So we'll be discussing these normal distributions quite extensively in the next few weeks. Okay, this is an ongoing New York Times experiment where every week they come up with a graph and they ask readers and students usually to see what's going on in the graph. We're going to look at what we notice, what do we wonder, what are we curious about, and what might be going on. So this is 2 histograms that were published. It's November 2018. So this was the ages of first-time mothers in 1980. You can see that in this case, this is obviously not symmetrical. This is a very skewed distribution here. And in this case, it has a slight rightward skew because you could see the tail pushes over to the right side. And then you can see the most common was around this age group, which actually is around, let's see, 18, 19 years old. Now let's compare that to 2016, right? To 2016, we have a strange phenomenon here, a dip in the age groups of 24 through 29, or 24 through 26, right? And then pick up again. What's happening in this case is it's almost become a slightly bimodal distribution where the center is somewhere here, except it's interesting because in the center there's a dip. Think more about this chart and see if you can answer some of these questions so we can discuss in our next session. Frequency polygon is our next type of chart. A frequency polygon is similar to a histogram. It also shows the shape of the distribution. It consists, however, of line segments that connect the class midpoints of class frequencies. So what you generate in order to create this frequency polygon is basically we take the midpoint of each class. So in this case, in the first class, if it was 200 to 600, the midpoint would be 400. So that would be plotted with the frequency in each of those classes. And notice we get this really nice polygon, basically, that shows a similar effect of what the histogram was showing. So here we're comparing the histogram to the frequency polygon. Now, kind of some of the benefits of the frequency polygon over the histogram occurs when you have to compare multiple data sets, right? So in this case, you'll notice that I've added another component here. This is Fowler motors in the blue. And notice we can kind of overlap these two results. So we have Applewood compared to Fowler motors. Well, a few things we can say just straight off the bat is, first of all, Fowler motors tends to have a much more closely clustered data set because notice the range is from 1800 to 3600, whereas our Applewood was basically 0 to 3600, okay, or 294 to 3292. Now, what else do we notice? We notice that this is a little bit more symmetrical potentially than our Applewood data set. And most importantly is that the center, or the average, is higher for Fowler motors than Applewood motors. We can definitely say that Fowler motors is more profitable than Applewood motors in this case. Now that information can also be done using the histogram, except it becomes difficult to kind of stack histogram. You'd have to put another one right underneath it, and then those little key differences would be a little bit more difficult to kind of pick out if you were looking at that shape. Finally, the cumulative frequency distribution. So the cumulative frequency distribution is again similar to a frequency polygon, but let's have a look at how this is built and put together. So to construct this distribution, we will be looking at this table that we created before for our data set, and a few things have changed. So for our profit section, notice that our class names have changed. So in this case, we're going to be looking at just listing the maximum. So in the first group, we're going to say all vehicles that received a profit of less than 600 are in the first class. The second is all vehicles less than 1,000. So what does that mean? Well, that means that the second class includes the 11 sold in the second class group that we found before, plus the 8 that were sold that were less than 600. By the time we get to less than 3,400, that should be exactly equal to 180, or our n number of observations. Let's see how this is plotted. So to plot this distribution, we scale the upper limit of each class along the x-axis and the corresponding cumulative frequency along the y-axis. And to provide additional info, we can label the vertical axis on the left units and vertical axis on the right as the percentages of the total. So in the Applewood auto sales, the vertical axis on the left is labeled 0 to 180 because 180 is the number of observations. And on the right, we just have 0 to 100. So let's have a look to see what that looks like. Here's our data. Here's our frequency polygon. Notice here that in the class of 600 or fewer, right, we had 8 sales, and that would be representative of 4.4% that we calculated before. In our last class, our very last class, less than 3,400, all our auto sales were in that group. Let's read this chart. First, 75% of vehicles sold earned a profit of less than what number? So let's start off going to our 75% line here. If we look at our 75% line, go to the cumulative frequency polygon, then go down to the x-axis, we can see that 75% of cars sold for a profit of less than $2,300. Let's look at it a different way. 60 of the vehicles earned a profit of less than what number? So then we can go to 60, go to the polygon, and down to our x-axis, and find that 60 of the vehicles earned a profit of less than $1,600. So this chart here, this data set, we're going to use it to basically work through a second example. I will show you the details of this on my as an iPad drawing. So we'll start off going through all the steps to create the histogram. Then we'll create a frequency polygon, and we'll create a cumulative frequency polygon as well. This is the end of lecture 2.